Having addressed the question of what fusion is, let's now have a look at some suitable reactions. I'll only include those which are favourable for artificial use and leave out the ones which occur in nature but which would be too difficult for us to produce on Earth. One good example of this is the hydrogen to hydrogen fusion which occurs in the Sun. In these equations, P is a proton, a hydrogen nucleus. Alpha represents an alpha particle, which is a helium nucleus. N is a neutron. D is a common stable isotope of hydrogen, consisting of a proton and a neutron called deuterium. T is tritium, which is an uncommon and radioactive and difficult to obtain isotope of hydrogen, which consists of a proton and two neutrons. And helium-3 is a similarly uncommon isotope of helium. 4 suitable reactions are shown on the screen. The first one is deuterium and tritium. This produces a neutron and an alpha particle and 17.6 mega electron volts of energy. There are 2 deuterium and deuterium reactions which are shown, and a deuterium plus a helium-3 reaction which produces a proton, an alpha particle and 18.3 mega electron volts of energy. Reactions which produce neutrons are called neutronic and are more tricky to deal with since, having no charge, we cannot extract energy from a neutron by slowing it down in an electric field. Instead, the neutrons are absorbed normally by a casing of lithium-6 around a reactor. This produces a reaction lithium-6 plus a neutron gets transformed into tritium and helium-4 plus 4.8 megavolts of energy. The resulting kinetic energy of these products can be absorbed by the lithium to produce usable heat. There are also several other, less favourable reactions, but ones which are distinct possibilities because they are aneutronic, that is, they produce no neutrons, just charged particles. One of them is boron-11 with a proton. This produces 3 nuclei of helium-4 and 8.7 megavolts. And another one is lithium-7 and a proton. However, to get some initial success, we would probably start with the most favourable reactions, and these are the deuterium-tritium reaction, the deuterium-deuterium one, and the deuterium-helium-3. Now, remember our fundamental equation which we saw in the last video. R is equal to sigma Na Nb times V. What we would like to do is to pick a value of particle velocity which gives us the largest reaction cross-section area, sigma, and therefore the one which has the best chance of fusion. The graphs of energy versus sigma have been found experimentally and theoretically and are shown below. As we can see, the deuterium-tritium reaction is the one to go for. Sigma is at a maximum at around 150 kiloelectron volts, which we can easily achieve by accelerating deuterium ions through an electric field of this value. This is not a particularly difficult task, and one which we discussed in the previous video. From this information we can work out the reaction rate R from the formula, or alternatively we can use it to calculate what particle density we need to achieve a particular value of R. If we do this for the DT reaction, we get the table which is shown. We could also note from this that if we didn't recover the 150 kiloelectron volts which we expended speeding up the deuterium, we would have to have a success rate of about 1 fusion in 35 particles to break even. That is for the energy in to be equal to the energy out. One major issue is that many of the particles coming into the reaction area will be scattered out of it by the repulsion between them and be deflected by other nuclei without fusing. Because only a bullseye will give us a fusion, we can see how many will statistically scatter by plotting the scattering cross-section on the same graph as before. This is shown on the screen. We can see from this that scattering is orders of magnitude more likely than fusion. So one conclusion is that the energy of the scattered particles must be collected and returned to the source, or there's no chance of the system working. And even when we do this, some of the scattered energy will be retained in the target as waste heat and not retrievable by the system. So here we have a situation. At a crude approximation, A particle fired into the target will either pass right through, or scatter, potentially warming the target, or fuse, generating energy. The question is whether it is possible to optimize these processes to get useful power out of the system.